Hello everybody, welcome to another lesson by me, Miss Pythagoras. In this lesson, I will explain how to prove more complex identities in trigonometry. This is lesson 2 of 5. We need to prove in the first example that cos to the power of 4a minus sin to the power of 4a is equal to cos 2a. Now let's start with the left hand side. And a very important thing is, can you see the algebra? So when you look at cos to the 4a minus sin to the 4a, that thing is the difference of two squares. So on the right hand side in flu algebra, can you do that one? If you factorize x to the 4 minus y to the 4, the difference of two squares, you end with, in a bracket, x squared minus y squared and another bracket x squared plus y squared. Now let's do that on trigonometry. On the left hand side, we can factorize and we end with, in a bracket, cos squared a minus sin squared a and cos squared a plus sin squared a, which brings us to, there's the formula sheet, and then I want to zoom in on this one. Cos squared alpha minus sin squared alpha is the double angle for cos 2 alpha. So when you go back to your first bracket, can you see it's the double angle? So that thing we can write as cos 2a. Then the next bracket, the cos squared a plus sin squared a, that one is very familiar from grade 11. That is equal to 1, the square's identity. So we can write it as 1. And what can you see? Cos 2a times 1 is cos 2a, and the left hand side is equal to the right hand side. Given is sin 2x minus cos 2x plus 1 over sin 2x plus cos 2x plus 1 equals tan x. Prove the identity. So then there's all the formulas from the formula sheet. Let's start with the left hand side, the more complex side. Now the first thing that you can see here on the left hand side, there's sin 2x, which is the double angle for sin, and the only option you have is that one. So we can write sin 2x as 2 sin x cos x. Then we find cos 2x. That's a double angle for cos 2x. We have three options on the right hand side from the formula sheet. Now my advice to you, since there's a tan x on the right hand side, I'm going to choose the one that contains the cos and the sin. So in other words, it's this one. But just be careful, there's a minus in front. So you write the minus and then the double angle inside a bracket. And then I can see where we're going with this one. Since there's a plus 1, we can also write in the place of plus 1 sin squared x plus cos squared x. Grade 11 identity. Everything over. Sin 2x, the double angle, there's only one option, so you can write 2 sin x cos x. And then again, there's a cos 2x, so that's the double angle for cos, and I think let's go for the one that contains the cos and the sin. Plus, in a bracket, cos squared x minus sin squared x for the double angle there, and in the place of plus 1, I'm going to write sin squared x plus cos squared x, the square's identity. Then in the next step, I'm going to multiply in the minus. So you end with the 2 sin x cos x minus cos squared x plus sin squared x plus sin squared x plus cos squared x, everything over. 2 sin x cos x, and then you multiply in the plus cos squared x minus sin squared x, and sin squared x plus cos squared x writes with. Now we can add like terms. So minus on top here, minus cos squared x plus cos squared x is nothing. And you're left with 2 sin x cos x and sin, this is this part, plus sin squared x plus another sin squared x is 2 sin squared x. And then on the denominator, what we can do is we can say minus sin squared x and plus sin squared x, they can cancel, and you're left with 2 sin x cos x, and then you can say cos squared x plus another cos squared x is 2 cos squared x. Now, let's see what is happening in algebra. If I give you this, 2ab plus 2a squared over 2ab plus 2b squared. We can factorize that one by taking out a common factor of 2a, and then we're left with b plus a over, and at the denominator we take out 2a as a, no, I beg your pardon, you take out 2b as a common factor, and you're left with a plus b, and then you can cancel out. So let's go back to the left-hand side to the trigonometry. So we will factorize. So on the numerator on top, we will take out 2 sin x as a common factor, and we're left with cos x plus sin x over, and at the denominator we take out 2 cos x, and we're left with sin x plus cos x. And then the 2 and the 2 can cancel. The cos x plus sin x, the whole thing, will cancel with the sin x plus cos x at the bottom. And then you're left with sin x over cos x, which is tan. Therefore, the left-hand side is equal to the right-hand side. Before we continue, have you subscribed yet? And a reminder, you can also visit my website www.onlinemaths.co.za. The link is in the comments below. There you will find all the chapters in the syllabus. Let's continue with the maths. If sin 76 degrees is equal to x and cos 76 degrees is equal to y, show that x squared minus y squared is equal to 62 degrees. Now, on the right-hand side, there's your double angles. Let's see what's going on here. Let's start with x squared minus y squared. Now, do you agree it was given that sin 76 is equal to x? So we can substitute x with sin 76. But it was sin squared. So all you do now is you also add a square there. Minus, and then y is cos 76. So you substitute y with cos squared 76. Then that thing looks as if it is the double angle for cos. But you must be very careful. If you look there on the formula sheet, cos, the double angle for cos 2 alpha is cos squared alpha minus sin squared alpha. The cos is in front. So on the left-hand side, in your sum, you first have to rearrange your two terms. So you can rearrange them. In other words, you write cos squared first plus the sin squared 76. But be careful, when you rearrange, the minus went with the cos squared. And then it's still not the double angle, since on the double angle, the cos is positive and the sin is negative. So what we have to do in our sum is we have to take out a minus as a common factor. And then you're left with bracket cos squared 76 minus sin squared 76. Now it's the double angle for cos 2 alpha. So in that thing's place, you leave the minus in front, and now it's, you write cos 2 for double angle, and then whatever this angle was, this is what's going inside the bracket there. So that's the double angle. Then you can say 2 times 76 is cos 152. And then you wanted the x squared minus y squared to be equal to sin 62. And we have a cos 152. So the thing that's worrying us is the 152. But we've got grade 11 tools. With that I mean reduction formula. So we can reduce the 152 with the reduction formula, the cos 90 plus 62. 90 plus 62 is indeed 152. And let me tell you, I was very glad when I ended with a 62 there, since what we want is sin 62. Now, there's a few problems. You must keep in mind that when you use the cos 90 plus reduction formula, then I'll do it here for you on your cast diagram. The 90 plus quadrant is this quadrant, and this quadrant is sin's quadrant. So cos there is negative. So when we reduce that thing, it becomes minus, in a bracket, minus sin 62 degrees. That's how you reduce it. And this minus is that minus. And then this is the angle 62. And remember, when we use the reduction formula 90 plus and minus, the name changes to the co-function. And you understand the negative, it's because cos in that quadrant was negative. And then you can say a minus times a minus is a plus, and there's your answer, plus sin 62. Another example. If tan 50 degrees is equal to k, evaluate 4 cos squared 25 degrees minus 2 over 2 sin 25 degrees times cos 25 degrees in terms of k. Now remember, when it says in terms of k, it means there can be a k inside your answer. Now let's start with that huge thing. So first of all, when you look at the numerator on top, the 4 cos squared 25 minus 2, it feels as if it could be the double angle for cos 2 alpha. But in the double angle for cos 2 alpha, this is a 2 and this is a 1. And now you're stuck with a 4 and a 2. So the first thing that you're going to do is you can take out 2 as a common factor. And then you're left with 2 cos squared 25 minus 1, which is indeed the double angle for cos 2 alpha. And then on the denominator, you have 2 sin 25 cos 25, which is the double angle for sin. So now let's see in the next step. 2, and then the 2 cos squared 25 minus 1 is the double angle for cos 2 times 25, and at the bottom, the 2 sin 25 cos 25 is the double angle for sin, and you end with 2 cos 50 divided by sin 50. Then the cos 50 over sin 50. You must be very careful. Tan is sin over cos, but now we have a cos over sin. So did you know that tan can also be written as the reciprocal? So a tan over 1, which is a sin over cos, is when you swap it around and you write it as 1 over tan, then you end with a cos over a sin. So on our sum, the cos 50 over sin 50 is the same as 1 over tan 50, the reciprocal of the normal tan, which is sin over x. And then it was given right at the beginning that tan 50 is equal to k. So now in tan 50's place, we can substitute k, and there's our question in terms of k. The answer, 2 over k. Last example. The question, prove that for any angle theta, cos 3 theta is equal to 4 cos cubed theta minus 3 cos theta. Whoa. And then there's a hint. Thanks for that. They tell you that 3 theta is the same as theta plus 2 theta. Now let's start with the left-hand side, cos 3 theta. Now, do you agree that the cos 3 theta, you can write it as theta plus 2 theta, since they gave us the hint. And then that thing is indeed the compound angle for cos alpha plus beta. Now we're going somewhere, so you can write that one as cos theta, cos 2 theta minus sin theta, sin 2 theta. Then it looks as if there's double angles. There's the cos 2 theta double angle, and which one to choose? Now, I chose the one with the sin, that contains the sin. So why did I do that? Since the rest of the sum, there's sin. That's what I thought. And then the other one, the sin 2 theta, the double angle there's only one option anyway. Sin 2 theta is to sin theta cos theta. Now, let's do it. So in the place of the cos 2 theta, I substituted the double angle minus sin theta, and then in the place of sin 2 theta, I substituted the double angle. Then, in the next step, now I can multiply in the cos theta, and I end with cos cubed theta minus cos theta sin squared theta. And then on the second part of my sum, I will multiply in the negative sin theta, and I end with negative 2 sin squared theta cos theta. Now it feels as if I'm going somewhere. Now, do you agree? Here, this is a cos and a sin squared theta with a cos and a sin squared theta. So, in fact, they are like terms. Therefore, I can add them and write it as cos cubed theta minus 3 cos theta sin squared theta. Then it feels as if I'm a little bit stuck. Now let's go to the original sum, and we can see that there's a 4 cos cubed theta minus 3 cos theta. So why I went back to that one was there's no sin. So my problem is to get rid of sin squared theta, and I've got a way. Grade 11 squares identity. I can rewrite that one as 1 minus cos squared theta. And then I can multiply in the negative 3 cos theta. And I end with cos cubed theta minus 3 cos theta plus 3 cos cubed theta. And then I find like terms. There's 1 cos cubed theta plus 3 cos cubed theta is 4 cos cubed theta minus 3 cos theta. And that is what they wanted. Now you know how to prove more complex identities. In the next lesson, I will explain how to solve basic trig equations. Click on the video in the left-hand corner to take you straight to the next lesson.